Hello everyone, welcome to another video tutorial on principles of electric machines and power electronics, a problem solving course. In this video, we start to solve the problems of the chapter 3, electromechanical energy conversion. So problem 1 of the chapter 3, in a translational motion actuator, the flux linkage versus current relationship is given by this equation. So this equation relates the coil flux linkage to the coil current. Also, we have this position variable x, right? We have one-dimensional motion. In this problem, we have an actuator and the mover can move only in one direction. Okay, so the range of x is given here. X is between 0 and 1 meter. I is the current in the coil of the actuator. Determine the force on the moving part at x equal to 0.6 meter. So when the value of x is 0.6 meter, how much electromagnetic force is applied to the moving part? So before solving this problem, let's review few first sections of the chapter 3 of the reference. Here, chapter 3, electromechanical energy conversion, section 1. So let's have a quick overview first and then we will solve the problem. There are various methods for calculating the force or torque developed in an energy conversion device. The method used here is based on the principle of conservation of energy, which states that energy can neither be created nor destroyed. It can only be changed from one form to another. Okay. As you remember from electromagnetic course, there are various methods for calculation of the force and the torque. Either electrostatic force or magnetostatic force, electrodynamic or magnetodynamic. Okay. We have methods such as Maxwell stress tensor, equivalent charge method, energy method. Okay, but the energy method is presented here in this reference, in this chapter. Energy method is a good method. You can calculate average values. Also, from numerical point of view, energy method is robust for calculation of force and torque, as we will see later in the ANSYS Maxwell. We have this problem 3. We will generate the model of the problem 3 in the ANSYS Maxwell and we'll investigate force calculation. Anyway, so an electromechanical converter system has 3 essential parts. 1. An electric system. 2. A mechanical system. And 3. A coupling field. In the case of rotating electric machines based on magnetic forces, the coupling field is the magnetic field, as shown in this figure. So here in this figure, you can see the flow chart of an electromechanical converter system. We have input electrical energy here and the output mechanical energy here. In the case of an electric machine, this is in motor operation, right? And in the case of generator operating mode, the direction of the power flow is reversed. Yes, in a generator mode, the mechanical power is converted to electrical one. Also, for energy conversion process, we have different loss types. Here we have electrical loss, or actually ohmic losses for the windings that we have in the structure. We have field loss, the hysteresis loss, and eddy current loss. Also, in mechanical parts, we have friction losses because we have moving objects. Yes, so we have mechanical losses. In the case of rotating electric machines, we have bearing loss and also windage loss. So for this electromechanical converter system, how we can write the energy balance equation? This is the energy balance equation. Electrical energy input from the source is equal to the output mechanical energy plus increase in stored energy in coupling field plus losses, energy losses. So this is the balance equation for energy conservation. So the electrical energy loss is the heating loss due to current flowing in the winding of the energy converter. This loss is known as I to R loss in the resistance of the winding. The field loss is the core loss due to changing magnetic field in the magnetic core. The mechanical loss is the friction and windage loss due to the motion of the moving components. All these losses are converted to heat. So thermal design of electrical machines is also very important. Okay, the focus here in this reference in this chapter is on electromagnetic design. We don't discuss thermal design. Okay, so the energy balance of this equation can be written as follows. If we segregate losses. So electrical energy input from source minus resistance loss is equal to mechanical energy output plus friction and windage loss plus increase in stored field energy and core loss. So we have this actually block diagram. This is the electrical system. Okay, so this is electrical system or electrical energy source. Yes, this is better. And we have a coupling field here, a coupling magnetic field, and finally this mechanical output power. So this is magnetic field, and this is the mechanical part or the output mechanical energy. I write here P out. If we have linear motion, the output power, is F force times the velocity. And if we have a rotating motion, we have a rotating object is torque times the angular speed omega. This is omega, the angular speed of the rotor. So here the input energy minus I to R loss, I to R loss, right? This energy is received in the magnetic field. We have increase in the value of the stored energy in the magnetic field. Also, we have losses, hysteresis loss, and eddy current loss. You know that we have P hysteresis and eddy current losses. This energy, right, is converted into mechanical one. Also, here we have mechanical losses, windage, and friction losses. And finally, we have net mechanical energy output. So this is motor operation. In the generator mode, the direction of the energy flow is reversed. But again, we have these losses also for the generator mode. So how we can rewrite this equation into a mathematical form? Consider a differential time interval. Okay, so we are going to write the energy balance equation in mathematical form, considering a differential time, delta t or dt. Okay, the total derivative. Okay, so I'm going to analyze this energy conversion process only for a differential time, a differential time interval. So during which, now consider a differential time interval dt during which an incremental total energy, electrical energy dWe, excluding I to R loss, flows to the system. So here we have these notations. WE is the electrical energy, WF is the field energy in the magnetic field, and Wm is the mechanical energy. You know the unit of the energy is joule. Okay, the unit of the energy. So for an instance of time, yes, for an instance of time, we can have this as a function of time. WF as a function of time, mechanical as a function of time. Okay, but for a time interval dt, let's analyze how much change we have in the value of these functions. dWe is the change in the electrical energy, right, that flows to the system during this time dt. Let dWf be the energy supplied to the field. So dWf is energy supplied to the magnetic field, either stored or loss. Okay, either stored or lost, or part stored and part lost. And dWm, the energy converted to mechanical form, again in useful form or loss, or part useful and part as loss. In the differential forms, this equation, okay, this is dWe, the input electrical energy minus resistance loss, is summation of these two. We can write dW, this is dWm mechanical one, dWe is equal to dWf plus dWm. Okay, so if you consider this red one, this is dWe, energy supplied to the magnetic field and this actually block from this system the net electrical energy delivered to the field. So this is divided into two parts: change in the WF and change in the mechanical energy, an important equation. Okay, we have here. So core loss are usually small, and if they are neglected, dWF represents the change in the stored magnetic field energy. Similarly, if we neglect friction and windage losses, mechanical losses, dWm will be available as useful mechanical energy output. Even if these losses cannot be neglected, they can be dealt with separately, as we will see in the next chapters when we derive the equivalent circuits for induction machines, DC machines, synchronous machines, and so on. So this is just an assumption. If we neglect losses, dWf is the change in the value of the stored energy in the magnetic field. And dWm is the change in the mechanical energy. So actually a lossless system. So consider this assumption for derivation of torque and force. In a well-designed electric machine, the percentage of loss should be much lower than the percentage of the net output power, right? Otherwise, the efficiency of the system is very low. The next section, field energy. What is the field energy? And what we mean when we calculate the amount of the stored energy in a magnetic field, in a permanent magnet, for example. Let's consider this simple example. However, you know this concept from electromagnetic course or from electric circuit theory course. You know what is the value of the energy stored in an inductor or in a capacitor, the electrical energy, right? You remember those equations. But now let's have a look for the field energy stored in cases that we have nonlinear materials, not linear materials. So consider the electromechanical system here in this figure. This is an example of an electromechanical system. So let me copy this image. Yes, this system that we have here. Considering this system, and consider that the movable part, this part is the movable part, this one, okay? And this is a stationary part. In the case of an electric machine, a rotating one, this is a stator and this is a rotor. In the case of this system, this is a movable part, a part that can move, and this is immovable part, the stationary part. Okay, so this is the air gap thickness. When this part moves to the right or to the left, the value of the air gap changes. Here you can see the reference position. Also, we can measure the movement of this part considering this variable gap or considering this reference position. No difference. Let us assume that the movable part is held stationary at some air gap. and the current is increased from 0 to a value I. Flux will be established in the magnetic system. Obviously, the change in the value of the mechanical energy is 0. Yes, correct. Because here we fix the position of this movable part and connect a voltage source here. So this is simply this circuit. We have a DC voltage source here. We have a resistor R. This is the resistance of the coil. And we have one inductor here. So the current I, when we apply this voltage, this DC voltage, the current rise up right to a steady state value. So in this process, how much energy will be stored in the magnetic field? Yes, energy is supplied by this source. We have this equation. dWe is equal to dWf plus dWm. dWm is 0 because we fix the movable part. We don't have any mechanical motion. So the change in the value of the mechanical energy is 0. And we have this dWe, the electrical energy supplied by the source to this inductor is equal to dWf. So how much is the dWe? If core loss is neglected, all the incremental electrical energy input is stored as incremental field energy. Yes, we have this equation. For inductor, we have this EMF is d lambda dt. If we neglect iron losses, all energy delivered by the source is stored in the magnetic field. What is the equation? Considering this EMF, this is dWe, E, I, D, T. Yes. So this is the equivalent circuit actually for the inductor. This is the voltage. This is the resistance. And this is EMF, E. That is d lambda dt, plus and minus sign. Also consider this current, I. Yes. So from circuit point of view, you can write this equation V equal to Ri plus d lambda dt. Okay. So if we multiply both sides of this equation by I, this is Vi is equal to Ri2 plus I d lambda dt. Okay. So this equation, yes, this is the electrical energy supplied by the source minus Ri2 losses that we have, electrical losses, electrical energy input from source minus resistance loss is equal to I d lambda dt, or actually IE. This is the power, right? This product is power. So this is the power delivered to the inductor, and the dWe, we should multiply this by differential time interval. So dWe is I d lambda, okay, or IE dt. This is dWf, the change in the value of the stored energy in the magnetic field, I d lambda dWf. This relationship between coil flux linkage and coil current for a particular air gap length is shown in figure 3. Yes, we derived this figure in one of the problems in the previous chapter. Yes, the coil flux linkage versus the coil current. This curve depends on the thickness of the air gap. When we change the value of the air gap, right, this curve will change. You know that. So here, this equation, the incremental field energy is shown as the cross-hatched area in the figure. When the flux linkage is increased from 0 to lambda, the energy stored in the magnetic field is this one. So if you integrate both sides of this equation, WF will be equal to 0 to lambda ID lambda. According to this equation, the field energy WF is a function of flux linkage. This integral from 0 to lambda I d lambda. This equation says that the stored energy in the magnetic field is a function of its flux linkage for an inductor. Depends on the state of the material, how much flux linkage we have for the coil. From mathematical point of view, this integral is equal to this area, the area between the flux linkage axis and the flux linkage versus current characteristic, this area. And this is the differential in the value of the magnetic energy, WF. Okay, so this equation explains the stored energy in the magnetic field in terms of circuit quantities, flux linkage and current. Can we rewrite this equation in terms of field quantities, right? In terms of magnetic field intensity and magnetic flux density or not? H and B. I lambda. Yes, these are circuit parameters. These are field quantities. Consider this structure shown here in the figure that we had. You can consider this mean flux line and write equations that we used in the chapter 1, integral of h dot dl. Yes, so you can write Ni is h core, L core, the length of the flux in the core, plus h gap, L gap. L gap is the length of the air gap. You know that the flux linkage is N times the flux in the core. Flux in the core phi is B times A, the cross section area of the core. You know that. So here, if you replace equations, this is I current. I, we can calculate I from this equation and flux linkage from this equation. So WF, the change, right, in the state of the material, in the stored energy, is calculated using this integral. So if you do the integration, finally we will have these equations. Okay, this is WF. This is integral of h core dB times the volume of the magnetic material plus b to the power 2 divided by 2 times mu 0 times the volume of the air gap. So here is the summary. We have this equation WF. This is a function of lambda. Is integral of from 0 to lambda I d lambda. In terms of field quantities, we have this equation. We have WF. This is a function of B. From 0 to B, if we saturate a core from 0 to B flux density, H dB. So here we should write this with capital W and this with a lower letter. Why? Because the unit here is joule and the unit of this integral is joule per meter cube. This is energy density and this is energy. So if I want to calculate energy using this equation, I should multiply this integral h dB by the volume of the material, right, that we calculated this integral for it. And if we have a linear material, the calculation is simple because for a linear material, you can write B equal to mu h. Or if you replace B in this integral, it will be equal to from 0 to B divided by mu dB. So this integral is B to the power 2 times mu. This is the value of the stored energy in a magnetic material with a linear permeability. Okay? And in the case of a nonlinear material, we need to have a BH curve and calculate this integral numerically. So here you can see the summation. WF, the energy stored in the magnetic field, is integral of H core dB times the volume of the magnetic material plus B to the power 2 divided by 2 mu 0 times the volume of the air gap. Because air gap is a linear magnetic material, we can calculate the integral. So what is this one finally? For this system, the energy stored in the magnetic field is the energy stored in the iron part plus the energy stored in the air gaps. We have two air gaps here. So here you can investigate this equation. Okay, so now let's review this section, energy and co-energy definitions. Until now, we studied definition of the energy, definition of the energy density, and now let's define a new parameter, a new quantity, that is co-energy. So this is a flux linkage versus I, this is H versus B, field quantities. We have this nonlinear curve for the material, this nonlinear curve for the inductor. The energy WF is defined as integral of I d lambda from 0 to lambda, and here W with lower letter we should write. WF energy density is integral from 0 to B H dB. This area. This is energy, and this is energy here for this case. Excuse me, here is energy density. Units are very important, and this is energy. So the lambda I characteristic of an electromagnetic system depends on the air gap length. And the BH characteristic of the magnetic material, okay, determines the HB curve. So here, yes, we know that when we increase the air gap thickness, actually we increase the value of the reluctance. We reduce inductance. So we have these curves. So you know that we have these curves. Let's, okay, this is better now. What is the equivalent circuit of this structure? This one. The equivalent circuit is this, the equivalent magnetic circuit. We have Ni, we have reluctance of the core, and we have reluctance of the gap. What is the value of the inductance? Is n to the power 2 divided by reluctance. So you know that inductance is the slope of this line. Okay, the slope of this line. Lambda is Li. So when the value of the gap is high, we will have this line. We will have this slope. The inductance is low. And as long as we increase the air gap, we reduce the air gap thickness, this is the direction of the increase in the value of the air gap. As long as we reduce the air gap thickness, the value of the inductance increases. When the air gap is 0, we have this curve. Okay, actually the reluctance of the gap is 0 and we have this nonlinear HB curve. And as long as we increase the air gap thickness, we have lower and lower values for the inductance. So how we can derive this characteristic using the ANSYS Maxwell? Let's check here. Let's use the structure of the problem 3, create this structure, then we discuss details when we solve this problem. So here simply let's add a new 2D Maxwell design. We have this stationary part, this is moving part attached to this spring, and we have this coil. So in this case, we can draw this rectangle. What is the width? 5 plus 10 plus 5, 20. You know this. We did it multiple times in the chapter 1. 20 centimeters. This rectangle. Let's draw the inner rectangle. The thickness of the vertical and horizontal limbs are the same, 5 centimeter. All dimensions are in centimeters. So here I can write 5 and 5 and 0. This is 10 and 10. Perfect software. So let's subtract these two objects. Yes. Now let's generate this moving part. So from here, let's draw this rectangle first in the middle. Yes, 10. That is correct. This is in the middle of this segment. Let me draw it again. Rectangle. Here we can see this triangle. So you can draw this. So select this one, subtract, yes. This is the stationary part. And let's draw the moving part, is this one. The moving part, I am going to define this parameter, the air gap thickness, to have a parametric model and change the value of the air gap thickness. So here, what is the coordinates of this corner point for this rectangle? This is equal to 10 centimeters plus gap, and the value of the gap, let's consider 1 millimeter. X size equal to 120 or 12 centimeters. Okay, so we have created this structure. This is the moving part. You can see this variable that we defined. If I set the value of air gap equal to 20, yes, 10, we can move this object. So let's generate geometry for coil arms like before. You know that. Here I am going to, yes, consider this as one coil arm and duplicate, mirror it. Okay, perfect. So select these two, change the color, and as you know, we should set the material to copper for these conducting regions. And here I am going to use this material. We used it before, magnetic alloy silicon core iron. Here you can see the HB curve of this material that we have. So yes, we defined objects, we defined materials. Now let's define the excitations. This is the first coil arm, this rectangle. What is the direction of the current for this region? Is into the paper. Yes, into the paper. The number of turns is 500. So here let's assign a current is 500 times coil current. What is the value of the coil current? I calculated the coil current here, 1.22 amps. We will discuss it later for the problem 3. And for another one, so this is the direction of the current into the paper. For this one, assign excitation. This is out of the paper, into the paper, out of the paper. Yes. So we defined the excitation. We set the material. We should draw the region. Consider 100% offset. Yes, for the enclosure. And then let's assign boundary condition. Select this edge, vector potential 0. Again, I select this object to define a fine mesh 1 centimeter. Okay, for write smooth calculations for the field quantities. Let's add the solution setup. We are ready to analyze this structure. So let's analyze and visualize flux density and flux lines. Solved, we can plot the magnitude of the B. Okay, here we have a high flux density in this sharp region. We can add this marker here. The value of the flux density is 0.67 Tesla. Also, you can select all objects and plot flux lines. Okay, the flux lines, you can visualize them. Anyway, so how we can calculate this flux linkage versus current characteristic? Simply, we should sweep over the value of the coil current. So here In optimetrics, let's define this parametric analysis. Add coil current. I am going to change the value of the coil current from 0 to 3 amps. The step size 0.2. So we are changing the current from 0 to 3 amps to calculate the flux linkage. Okay, so add current from 0 to 3. The step size is 0.2. Add everything the same. Save. I need to define this matrix if I want to calculate the flux linkage. The number of turns 500. So group 1. Yes, this coil. We did these settings multiple times in the chapter 1. So, okay, let's clean up all previous solutions and run this parametric analysis. Then we can plot the flux linkage, the coil flux linkage versus the coil current for this structure. Okay, simulation completed, and from here, mag flux, you know that we need to multiply this by the stack length. The stack length in this problem is 5 centimeter also. Here I multiply this by 5 centimeters divided by 1 meter. That's all. The primary sweep is the coil current. And here we have this flux linkage versus current for this object. If I increase the value of the current and we have a deep saturation, so we can have something like this. But how we can change the value of the air gap thickness? In this parametric analysis, we can also sweep over the value of the air gap. So if I add the gap, let's change the value of the air gap from 1 millimeter to 3. Step size 1. And modify this one. I want to change the coil current from 0 to 5. Step size 0.25. Update. So we have this calculation table. So again, clean up the solutions and run this parametric analysis. In this case, we change the value of the air gap thickness and we calculate the flux linkage versus current characteristic. This is important simulation, and you will see how we use this simulation to calculate the value of the force, the average value of the developed force in a magnetic structure. So, simulation completed. Now let's modify this plot. I want to generate the plot for all air gaps. Select all, apply, trace. Perfect. As you can see, here the red one is when the air gap is 1 millimeter. This is when the air gap is 2, 3. Yes. So as long as we increase the air gap, this becomes a line. Yes, because we don't have a deep saturation in the core due to the high air gap. The air gap reluctance is much higher than the reluctance of the iron. Yes. But when we decrease the value of the air gap, the reluctance of the air gap becomes close to the reluctance of the iron. And we can see this nonlinear characteristic. Anyway, this one that you can see it here. For a particular value of the air gap length, the energy stored in the field is represented by the area between lambda axis and lambda characteristic as shown in this figure. This is the energy. The area B between the I-axis and lambda I characteristic is known as the co-energy, this one. So this area is energy, and we can define a new concept, co-energy, this area. We can show it using this WF prime, the co-energy. This is from 0 to I. This is lambda di. The energy is a function of lambda. The co-energy is a function of current. Again, we can define the same here for field quantities. The co-energy density is integral of from 0 to h b dh. This is joule per meter cube. Again, this is a function of b, and this is a function of h. Four important equations that we have in this chapter. Okay, four important equations: energy, co-energy, energy density, co-energy density, flux linkage, current, flux density, magnetic field intensity. So this quantity, co-energy, has no physical significance. However, as we will be seen later, it can be used to derive expressions for force or torque developed in an electromagnetic system. Finally, we have one important equation. In the ANSYS Maxwell, if you check the calculator, you have access to all of these parameters. Co-energy, energy. Yes, you can calculate the total energy in the stored magnetic field in the ANSYS Maxwell and co-energy. Yes, so we have access to these quantities in the software also. We have this for a particular value of I and lambda, W F plus W prime F is lambda times I. This is the area of this rectangle actually. Yes, you know that the area of this rectangle is lambda times I, this equation. And so, yes, this is summation. I think this is a typo error. Okay, this is a summation. And here we have energy density WF plus WF prime is B times H. Energy density plus co-energy density. In the case of a linear material, this is a line, and in the case of a linear material, the energy is equal to co-energy, that is equal to lambda I divided by 2, or BH divided by 2 in the case of a linear magnetic material, WF prime. We have this typo error here anyway, you can check that in this reference. So this is right important derivation. So now let's check. We have this inductor. This is an inductor. How much is the value of the stored energy in it? If we assume a linear material for it, WF is equal to 1 divided by 2 lambda I. Lambda is Li, so this is 1 divided by 2 Li2, or 1 divided by 2 lambda 2 divided by L, energy stored in an inductor, a linear one. Okay, we have similar equations for capacitor. Yes, in a magnetic system, if we have this equation, integral of H dB for electric system, we have what, right? We have electric field and charge density. You can review equations from the electromagnetic book reference that you have. Anyway, so how we can use these definitions to calculate mechanical force or mechanical torque? We need to consider a system and write equations and check the motion this time. So again, consider this system. Let me copy this. Okay, consider this system. If we have motion in this system, suppose we apply a voltage source here, so we will have current, we will have this magnetic field, and we will have attraction force, right? Attraction force in this direction. So if we consider a situation that the gap changes from G1 to G2, okay, how we can calculate the average value of the developed force? Yes, how much is that? So here again we can draw this characteristic lambda I. If we have the initial position for this moving part, if the gap be equal to G1, we can derive or we can calculate this curve. Okay, this is when gap is equal to gap 1. When we excite the coil and we have attraction force, this moving part moves in this direction, and suppose the new position, the gap new, is G2. So this one. Okay, in this case, again, for the new position, we can calculate the lambda I characteristic. So how we can show this process? I mean, from zero voltage, zero current to the new state in the material that we have. So in the first case, when the gap is equal to gap 1, here gap is equal to gap 2. Suppose the system is in the steady state and the value of the flux linkage is lambda 1. Lambda 1. Then when we have a movement, okay, the after movement and after having the steady state, for the new value of the air gap, the value of the current again will be I. What is the reason? Because we consider a fixed value for voltage here, for the voltage here. The value of the resistance is fixed. So in the steady state operation, we don't have EMF. The value of the current is the same, right? For gap 1 and gap 2. So we can propose different trajectories. So to model this movement, we can have this trajectory. Let's show it with this color, this trajectory. We can have this trajectory. Okay, we can have different trajectories to move actually from point 1 to the point 2. But if you consider a differential time. And if you consider that the system is lossless, we can have two spatial trajectories. This is the first one. This is the first one. This one. For this trajectory, the value of the current remains constant, and we have the change only in the value of the flux linkage of the coil from lambda 1 to lambda 2. Okay, this is one case. This case is when the movement happens in a long time, right? The movement is slow, and we can confirm that the current will remain constant during the movement. So here we have the case. Here we have the case. If the movable part has moved slowly, the current has remained essentially constant during the motion. The operating point has therefore moved upward from point A to B, this point to this point, as shown in this figure. So this is the special trajectory one that we have. Movement is very slow and the current remains constant, right? We move along this trajectory. So now let's use the energy balance equation. The energy balance equation dWe is dWf plus dWm. How much is the value of the dWe? You know that it is equal to this one, E I dt or I d lambda, when we move from A to B, from lambda 1 to lambda 2. So in this case, this integral is area of this rectangle. Okay, the area of this rectangle. So here, let me show this area by this color, this orange color. This is dWe. Okay, dWe that we have. And what is the dWf? dWf is equal to this area. When the lambda is equal to lambda 1, the stored energy in the magnetic field is this one, this area. Okay, and when lambda is lambda 2, this is the stored magnetic field, this green one. Okay, so this is the change in the value of the stored energy in the magnetic field, this one. In this case, you can see the trajectory, this area, 0 B C, this area minus this area, 0 A D. Okay, so you can consider that. So how much is the change in the mechanical energy? So dWf is hatched area, blue minus the green one. So dWm is equal to dWe minus dWf. That is actually this area, this hatched area, 0 AB. Okay, this area is dWm. This area is equal to the change in the value of the mechanical energy. Yes, so we have this. So how much is this area? This area, we can use the co-energy definition. So this area is equal to the change in the value of the co-energy. Okay, so this is gap equal to gap to I lambda, and this is gap equal to gap 1. So this area I is constant, and this area, this one, is the change in the value of the co-energy. Yes, this one that we have. The change in the mechanical energy is the change in the value of the co-energy. So how much is the change in the value of the mechanical energy? Is F times dx, the distance of the movement. Force times distance is energy. Yes, force times distance. Work, mechanical work. The unit is joule. So finally we have this equation. The force is the partial derivative of the co-energy with respect to this position coordinate that we have, where the value of the I is constant. So this is the case 1 if we consider this trajectory. And we can consider another trajectory. We can consider another case. Suppose the movement occurs very fast, very fast, in such a way that during the movement we don't have any change in the value of the flux linkage. This trajectory, right? So when the movement occurs very fast, the flux remains constant. So if we write the energy balance equation again, dWe equal to dWf plus dWm. In this case, dWe, that is equal to this integral, this one. We don't have any change in the value of the lambda for this trajectory. Okay, the change in the input electrical energy. So dWe is 0, and dWm is equal to negative of dWf. Again, we have Fm dx equal to dW negative of dWf, and Fm is negative of partial derivative of energy with respect to x, this equation. Again, we have a typo error here. You should consider a negative sign here in this equation. Let us now consider that the movement has occurred very quickly. It may be assumed that during the motion, the flux linkage has remained essentially constant as shown in this figure, this trajectory. So in this case, we have this equation, and this is the value of the force when the flux linkage is constant. So in summary, we have these two important equations for the force. We can use energy or we can use co-energy, depending on the type of the problem, okay, formulations that we have. The developed magnetic force is partial derivative of co-energy when the value of the current is constant, or Fm is negative of partial derivative of energy when the value of the flux linkage is constant, the value of the flux linkage. Why partial derivative? Because we know that energy is a function of lambda and x. Here, co-energy is a function of current and x. Okay, so you can consider this change in the value of the field energy and co-energy. So from the calculus, you know that when we have this two variable function, lambda and x, the total derivative dwf, the change in the value of the wf, is equal to partial derivative of f with respect to lambda d lambda plus partial derivative of f with respect to x dx. So here we know that dwf is equal to dwe minus dwm, and we know that dwe is id lambda, dwm is fm dx. So fm, the force is fm, the magnetic force is negative of partial derivative of energy with respect to x, and current, coil current, is partial derivative of energy with respect to lambda. Yes, again, we have this important equation. Similarly, you can derive the corresponding equations for co-energy. And for co-energy, find a relationship between current and flux linkage. Perfect. You can extend this formulation when you have a multi-excitation system. Anyway, a good review. And when we use ANSYS Maxwell, you can realize these important equations much better. This is a very important chapter. Okay, so you should read this chapter very carefully. So now let's solve the problem 1. The flux linkage, right, and current relationship is given here. I am going to use energy definition to solve this problem, to calculate force. So here we have this equation. What was definition of the energy? Energy is a function of the flux linkage and x, integral from 0 to lambda I d lambda. So replace I from this equation, and if we take right integral of this expression, replace the boundary points, we will have this equation. So this is the energy as a function of the flux linkage and x. What is the value of the force? We should take the partial derivative of the energy with respect to x, -1. So if we take the partial derivative of f with respect to x, we will have this. Finally, you can replace x, calculate the force when x is equal to 0.6. So if we replace this number, we will have this equation. The value of the force is lambda to the power 2. So let's check the solution from here. The first problem of the chapter 3, the FM force. And now let's solve the problem 2. The flux linkage versus I relationship for an electromagnetic system is given by this equation. Again, we have a relationship between the flux linkage and the current. Also, we have this position variable, G. This is the gap, where G is the air gap length. For current I equal to 2 amps and G equal to 10 centimeters, determine the mechanical force on the moving part. A, using the energy of the system, B, using the co-energy. Okay, the relationship between the flux linkage and current is given, and we should calculate the force using the energy formulation and co-energy formulation and compare for this specific operating point. The values that we calculate for the force must be the same. Okay, both formulation must result in the same value for the force. So this is important. Here, if we use energy formulation, we can write energy is a function of the flux linkage and gap integral from 0 to lambda I d lambda. You can replace I from this equation here, and that is lambda gap divided by 1.2 to the power 2. Calculate this integral. We have this for the energy, and the force is negative of partial derivative of the energy with respect to the position variable. In this case is gap. So this is the value of the force. And I am going to calculate the force using this equation when the gap is 10 centimeters and current is 2. We don't have flux. Yes, the relationship is given here. The flux as a function of current and gap is this one. So for this operating conditions, the value of the flux linkage is equal to 16.97 Weber. You can replace numbers to this equation. Yes, the value of the force is negative 226.2 Newton. Okay, this is calculated using the energy method. What about the co-energy? The co-energy is a function of current and gap integral from 0 to I lambda di. Now you should replace lambda as a function of the current. So this one we have, you can calculate the integral. This is the integral of this expression. What is the value of the force is the partial derivative of the energy with respect to gap. We have this. So if you replace the numbers, the value of the force again will be equal to negative 226.2. This is the important point of this problem that you should keep it in mind. Not important you use energy formulation or co-energy formulation. Both methods must result in the same number for the value of the force. Okay, so I think the time of this video is high. So before going for the next problem, problem 3, it's good to review the chapter 3, the sections that we studied together, and solve these two problems again. Then we will solve this problem and try it in the ANSYS Maxwell software and check the numbers. So let's continue in the next video.